This video is for the revision of ionic bonding. Okay, so ionic bonding, its definition is that it's the attraction between oppositely charged ions, one positive, one negative. So generally in the IB syllabus, things that have a difference in electronegativity of more than 1.7, so more than that, then it's an ionic bond. Let's go to the data booklet and see some examples. Although in the IG syllabus, you might have this general sweep that metals and non-metals will form ionic bond and non-metals will form covalent bond. That is not always true. Now that you're in the IB syllabus, now it's more detailed. So we're going to use these electronegativity values to find out whether it's ionic or covalent. Okay, something that is very common that we've seen before. So let's say aluminium, a metal, and say fluoride, a non-metal. So 4 minus 1.6, we get 2.4. So this is ionically bonded. Okay, but in the same group, so one metal and one non-metal, in the same group, AlCl3. Okay, Cl is 3.2 and Al is 1.6. The difference is only 1.6. So this is covalent. So AlCl3 is covalently bonded, while AlF3 is ionically bonded. Some things have ionic with covalent characters. So the bond, generally we say that they're ionic, but they've got covalent characters. For example, if I have Be with O, so 3.4 minus 1.6, that's 1.8. It's just slightly above 1.7, so it is ionic. But it shows covalent characters. So a little bit of covalent characters, although we say that it's ionic. Same goes for Al2O3. It's ionic, but it has some covalent characters. Unlike AlCl3, it's fully covalent. Back to how an ionic bond is formed. So it must have oppositely charged ions. We look at the cation first, then the anion. Cations, they are smaller than the original atom because they lose an electron from the outermost shell. So for Na, for example, so this last shell is gone when we remove this electron. So it is smaller. And the number of protons didn't change, but the number of electrons is now less. So it pulls harder, so it's smaller now. And this is an Na+. The electronic configuration would be 1s2, 2s2, 2p6, and the 3s1 is gone. So we take out the electrons from the outermost shell always. An anion, on the other hand, it becomes bigger after it received the electrons because the number of protons didn't change, but we add one electron, so it's harder for the protons to hold the electrons in, so it became slightly larger. So in some ways, we can see it as if this electron from the Na came to the chlorine here. So then they are oppositely charged. Na becomes positively charged and Cl becomes negatively charged. So there's an attraction between these oppositely charged ions. That's an ionic bond. Let's look at this picture here. So this is how Na and Cl is arranged in its lattice structure. So it's Na, then Cl, Na, then Cl. It's arranged very tidily. And let's look at the one in the middle. That is an Na. So I put this yellow as Na+. And let's see how many of the Cl- is touching that Na+. So up and down, right and left, front and back. That makes 6. So the coordination number would be 6 for this ionic lattice structure. That is what you mean by coordination number. Usually when these ions are formed, they want to be isoelectronic with a noble gas. That means the same electronic configuration or same number of electrons with a noble gas. But for transition elements, transition metals, they can form more than one ion, more than one type of charge. So like, for example, there is Fe2 plus and Fe3 plus, and we must remove the electrons from the outermost first, which is that 4s2. So 4s2, the 2 electrons were taken out first. And once it's taken out for Fe3 plus, we take out one more from the 3D. So these are its electronic configuration. And therefore, it can form FeCl2 and FeCl3. Let's look at formulas. Let's look at some examples of the formulas of ions and what is its formula for the ionic compound. So let's say I have an ammonium here with sulfate. So ammonium and sulfate. So we cross, so it will get NH4, 2 of it, because it's only 1 plus, and SO4, 2 minus. Next example, Mg2 plus, say with phosphate, PO4, 3 minus, cross. So Mg, we need 3 of it. PO4 will need 2 of it. So what's the charge actually? If I have 3 pieces of Mg, then I will have 6 plus. And if I have 2 pieces of PO4, then I will have 6 minus. That's how it becomes neutral like this. Next example, say if I have Al 3 plus and maybe a CO3 2 minus cross. So Al I get 2, CO3 3 of it. Fe2 plus with OH negative cross Fe1 OH2. And last Fe2S3. Let's look at the properties of ionic compounds. The volatility, it's not volatile because it have a high melting boiling point. The reason is because ionic bonds are very strong. We need lots and lots of energy to overcome that strong electrostatic attraction, because it's a positive ion and a negative ion bonded together. So they have very high melting boiling points compared to some of the weaker bonds. Although the ionic bond, ionically bonded compounds, they're very strong, they've got good strength, but it's quite brittle in a way, because if you were to hit this, so this layer will dislocate, and then the positive will be facing the positive when it dislocates, because this will move here, and this yellow one will move here, and this purple one will move here. So as you can see in this picture, it's plus, plus, and plus, minus, minus, and minus. They will repel each other, so it will break. Therefore, ionic compounds, they are brittle. If you look at this picture again here, so they are nicely arranged in its lattice structure, plus facing the minus, very tidy. So electric cannot pass this nicely arranged structure. So it cannot conduct electricity when it's held in solid like that, because it's so tidy, the charge plus and the minus are facing each other. But if you mess it up like this, then electricity can pass because the ions become mobile. So if you were to put a negative electrode here, then the positive will be attracted to it. And if you put a positive electrode here, then the negative will be attracted to it. And let's discuss its solubility. So for example, NaCl. So NaCl, it would be soluble in polar solvents like water, but it's not soluble in non-polar solvents like CCl4. The reason is because they can't bond with each other. So if I have an NaCl and this water here, O is slightly negative and H is slightly positive. Therefore, the Na will be attracted to the O, and Cl will be attracted to the H. So these bonds formed are called ion dipoles. Ion from the Na plus or Cl minus here, and dipole from the water. Although the bonds are polar in C and Cl here, but they cancel out the tetrahedral shape, so they're cancelled out. So there is no permanent dipole in CCl4, so the Na and the Cl is not attracted to it, so it's not soluble in non-polar solvents. Ionic liquids are salts that are in liquid state, and they've got melting point that is below 100. Since it melts below 100 degrees Celsius, so it's liquid. And for example, this NR4Cl tetraalkyl ammonium chloride, let's draw it here. It looks like an ammonium except with a CH3. And here it is ionically bonded. And these can dissolve a wide range of inorganic or organic compounds. So it's a very good solvent since it's a liquid. It has very little vapor pressure and can be reused.